Hello, folks. Welcome back to Chemistry 132B, lecture number 7. And we will be picking up right where we left off last time. So I don't know if you remember, but we talked about an electron that is in a box, and we tried to solve the Schrödinger equation for that particular situation. And if we did that, we found a couple of solutions, and those solutions were sine waves, and we also found the energies associated with those wave functions. And the energies, as we noticed, were discrete, and they had a certain separation between consecutive states. That was a true character of quantum mechanical behavior. So the combination of having wave-like properties and being confined, which is exactly the situation we're having with electrons in atoms and molecules, led to discretized energy levels. And that is a very important finding that we will be using as we move on in this class. So before we continue, I'd like to kind of give you a little bit of a feel for how these things can be understood. So here you see in this picture a very simple setup. It's a piece of rope, really. And on one end, it is being shaken by something that shakes. And then on the other end, it is being confined. Okay, so you can think of this as follows. On the left and on the right side, you are basically fixing the rope to fixed points. They can't move. It can't move at the beginning on the right. It can't move at the start on the left either. So it's confined in a way. And then when I'm starting to shake it, of course, what you get is standing waves. Okay. So in the following picture, you can see an actual photograph of this setup. This is with a time shutter open for a while, so you can see very nicely these standing waves. What I like about this picture, if I think about electrons that are sitting in a box, which basically assume the same kind of standing waves, I have the same kind of idea of where the particle is. If the particle is truly a wave, if the particle behaves like a wave, and if I'm asking myself, where is the particle? Then the particle is basically everywhere where the wave is, right? So it's not in a fixed location. It's definitely not true that you should think of this as an electron that is tracking the shape of the wave as a function of time. So going from left to right and tracking the shape of the wave. That's not the case. In fact, the electron is the wave. And as you can see here, the wave is throughout the box. It's everywhere. If you ask me, where is the wave is not in one location. The wave is the entire thing. And this is the same way that you can think about the electron being in the box. The electron is really everywhere at the same time with a certain probability, right? So don't think of it as a little tiny point that is zipping back and forth in the box. Think of it, if you put the electron in the box, the electron itself changes character. And it does not become a fixed point in space, but in fact, it is spread out in space with a certain probability that has the shape of a wave. Okay, so if you look at the standing waves we can make in this particular pretty simple scenario of a piece of rope between two fixed points, then you can see that you can form the standing waves on the right. And this is exactly kind of like what we see in the particle in the box, right? So similar kind of standing waves we form. Because the situation is quite similar. We just confine and we demand that the amplitude of the wave disappears at the edges. That's exactly the same stipulation we had in the quantum mechanical box. And consequently, the wave shapes that we find that are valid solutions are very similar to the standing waves you see here. So if you take that picture and then you kind of move it into 2 dimensions, okay? So let me show you an example of a 2-dimensional wave. What is a 2-dimensional wave? Well, they're all around us. Here's an example of the soundboard of a guitar, okay? So this is a very nice experiment. You can do it at home. If you have a guitar, you can put some loose sand on the soundboard and then pluck one of the strings, and what you see is you see the sand basically assuming certain shapes based on the modulation of the soundboard. Okay, so you can visualize really the shape of the waves. So this is a 2-dimensional wave. You see it has a large amplitude in some regions and weak amplitudes in other regions, right? So It's just an extension of a one-dimensional wave into 2 dimensions. Now, this is, of course, a soundboard on a guitar that has nothing to do with an electron, but the same kind of distribution you may expect at the scale at which the electron lives. So here's a kind of an experiment which is much more difficult to do than the soundboard of a guitar, but you can do it nonetheless. Here, people have managed to put atoms, I think these are iron atoms, that are put in a particular pattern on a surface. I think the surface is a copper surface, if I'm not mistaken. And what happens is you have electrons that are so-called confined to the surface. These are called surface electrons, and they form basically a sea of electrons. But if you put like a barrier around it, then these electrons are kind of confined in 2 dimensions. They can still move, but they assume wave shapes. And you can see inside the barriers, you can see a pattern that is an interference pattern. It's kind of like a standing wave pattern, but now in 2 dimensions. It's even more clear, I think, on the right-hand side, where you see a circular barrier. And in the middle, you see this beautiful standing wave pattern. If you ask me, what is that? Then the answer is, that is an electron, okay? That is basically the electron that is confined and has to assume a certain shape. This is the probability of seeing an electron when it is confined on a surface. Okay, so there are regions in space where it's unlikely to find the electron. There's regions in space where it's very likely to find the electron. In fact, in the middle, there is a pretty high probability of finding the electron, but immediately around it, there's kind of like a dimple, and that is where you will not find the electron. This is a direct consequence. Of stems, it looks like. Okay, I think I'm back. This remains a challenge, folks. I'm here at the university using university internet, but it's still not good enough in some cases. So apologies for that. So in any case, you see a few more realizations of the same idea, where you see electron waves on a surface, and clearly the kind of the patterns that you see are the patterns of a 2-dimensional wave. So this is also something we would expect if we think of an electron in a 2-dimensional box. Okay, so let's see how that translates. So if we, okay, let's say, go in here. There's many things going on behind the scenes that you don't know about, but it looks pretty bad from here. My iPad doesn't work. My computer froze. It's too bad. Okay, so what are we talking about? We're going to talk about basically an electron in a 2-dimensional box. Okay, and what we can say is that in that case, we have a Hamiltonian that we can write as follows. So it's now a 2-dimensional Hamiltonian. Okay, and so previously we had this kind of second-order derivative with respect to x, but now we also have a second-order derivative with respect to y, like so. Now in the box, so remember this is a 2-dimensional box, so it's a square box like so. Okay, and on the edges there are potential barriers. Okay, so around it there is a potential barrier. But inside the box, inside the potential is going to be 0. Outside the box, the potential has a certain value. okay? And I can put that value to infinity if I want to, okay? And that's what I'm going to do, just like last time. I'm going to demand that the potential outside the box reaches infinity so that the particle, the electron in this case, can't go there, right? So now I'm asking myself, what are solutions to this Hamiltonian eigenvalue equation, which of course looks like so. So I'm trying to find now a wave function, which is a function of 2 dimensions. And I think I'm going to find an energy, okay? And the energy now has 1, n2, so n1, n2. It has now 2 indices because there's 2 dimensions. So I get 1 more index. So the solution to this is actually surprisingly simple, okay? And it's very similar to the solutions that we found last time. In fact, it is simply a multiplication of 2 particles in a box, okay? One that moves in y and one that moves in x, like so. And what I find, therefore, is an amplitude in x, amplitude in y, and then exactly the same functions we saw last time, which were the sine functions with nx, pi x over L x, that's the length in dimension x, it's the length in dimension y, and then times the sine function for the y direction, ny and pi. Oops, that should be y, L, y. Let me just redo that. It should be a y. There. So ny pi y. Y is the running variable, and ly is the length of the box in the y dimension, of the square box in the y dimension. Now the beautiful thing here is that the energy, if you plug this thing into this 2-dimensional Schrödinger equation over here, then you find energies. And the energies have now 2 indexes. I can call them, let's call them nx and ny, because that's what you wrote here. So let's make this an x and a y, just for consistency. Then we can see that, in fact, we have the solution for nx plus the solution for ny, okay? And these are solutions exactly the same as last time. So we can write the solution straight away. Okay. Oops, let's not do that. Let's not do that. Let's do it this way. N squared over the length of the box in x plus ny squared length of the box in y. So basically, the first one here is ex, the second one is ey, right? And the solutions have exactly the same shape as before of the 1-dimensional box. The reason why this works is because these dimensions are exactly orthogonal. So whatever happens in y is independent of what happens in x, right? And so therefore, it is simply a multiplication in terms of the wave functions. So the wave functions are simply a multiplication of the 2 wave functions that are independent of one another because they are on orthogonal coordinates. And if you substitute this wave function in the Schrödinger equation, you find that the energies are a sum of the individual solutions, the solution along x plus the solution along y. Okay. So something interesting is happening in this case. Let's look at an example. Let's look at an example where I have nx equals 3 and ny equals 1. Okay, just an arbitrary selection of possibilities because n, if you remember, runs from 1 to infinity in integer steps for both of these indices, both nx and ny run over that interval. So I can now look at a wave function that has the following indices, 3 and 1. So psi 3, 1, okay, where nx equals 3 and ny equals 1. What does it look like? Well, it looks like an amplitude. This is a normalization constant, let's say, A1 and A3. And then the sine functions, where I just fill out the 3, because that is nx equals 3. And then L, and I assume here that the box is square. Okay, so Lx equals Ly. That makes it a little easier. And that turns out to be important, in fact, in a moment. Okay, so this is the solution. And the energy of this wave function is as follows. Okay, so that is also 3, 1. That is h squared 8m. And because the L's are the same in both directions, I can take them out. I find 3 squared plus 1 squared. And, that is 9 plus 1. That's 10. So I find 10 h bar, not h bar, just h squared 8ml squared. It should be a square here. Okay, so that is a solution to be fine. All right. Now, interestingly, if I have the following, I switch the labels. So I make ny 3 and nx, I make 1. Okay, so that will be a wave function 1, 3. So I can write that out as well. Let's do it very quick. Looks like this. Basically, you swap the labels. So it's going to be pi x over L, and then sine of 3 pi y over L. And the energy here is actually the same. Oops. 1, 3. The energy is the same. 8ml squared, because it's now just 1 squared plus 3 squared, which is the same number, 10 h squared over 8ml squared.
Perfect, okay. Sir.
Yeah.
Is this only true because it's a square box, right? Because we assume that Lx and Ly are equal to each other, right?
Yeah, absolutely correct. That's a great observation. It's true because I chose a square box where Lx equals Ly, and that's why these two energies are the same. Okay, because if I do not make them the same, then this is not the same. If I switch the labels, then it's not the same because the L's are different. All right, so that's why it only holds for a square box. But this is an important observation, in fact, and that means that if you have symmetry in your system, okay, if you have symmetry in your system, then you also have situations where energies of different states can be the same, as is indicated over here. These are two different wave functions, okay? They're two different solutions of the Hamiltonian, but they do have the same energy. And that results from the fact that there is a certain amount of symmetry in my system. So in general, in quantum mechanics, if there is a high degree of symmetry in my system, I will find similar energies for different wave functions. And there's a special word for that in quantum mechanics, and that is degeneracy. Okay, it's a very strange word, but degeneracy means that two or more wave functions have the same energy. Okay, two or more wave functions have the same energy. So these two wave functions here, these two guys, are degenerate wave functions. They are different states, different solutions of the Hamiltonian, okay, different eigenstates of the Hamiltonian, but they have the same energy, they have the same eigenvalue, and therefore they're called degenerate states. And we will see examples of that later on when we look at the wave functions of an atom, of an electron that is bound to an atom. We'll see also a high degree of degeneracy in that system, which is kind of understandable because the atomic system is, of course, very symmetric. It has spherical symmetry, and therefore, but just based on that observation alone, we can probably predict that we will find a high degree of degeneracy. And if you don't believe that, think about what you know. This is a little bit foreshadowing. Think about what you know about, for instance, p orbitals or d orbitals. Okay, if you have a set of p orbitals, they come in sets of 3. right? There's 3 p orbitals, there's 5 d orbitals, okay, for each principal quantum number n. And that means that there is a degeneracy already going on there, because you have 3 wave functions in the p subshell that have the same energy, even though they're different solutions to the Schrödinger equation, right? So those are degenerate states. Okay, so let's have a look at some pictures to kind of visualize that. So here are a couple of examples. Here you see a square box, okay? You can just put the solution into, you know, a kind of a mathematical plotting program. You can do Mathematica if you're familiar with that. And you can just write out the formula I just wrote on the screen and plot, for instance, psi 1, 1, okay? And if you do that, you find this shape. So you see a 2-dimensional box, you see a 1-dimensional wave that is the same in each dimension because it's 1, 1, and therefore it looks like a dome shape, okay? If you do the square modulus of this shape, then you find the probability of finding the electron anywhere in the box. So this is the electron wave. This is the electron wave of an electron that is stuck in a 2-dimensional box. This is what it looks like. This is what an electron looks like when it's stuck in a 2-dimensional box. If I change one of the indices, let's say y to 2, then of course y will now have an extra swing, because n equals 2 means that there is a swing up and a swing down, and that happens only along the y dimension, not along the x dimension, and therefore this 2-dimensional wave function looks different. Okay. Here's another one. These two are degenerate. Okay, you can see already the shape of the wave functions are not exactly the same, but they are related. In fact, they are related by a rotation of 90 degrees. As you can see, if I rotate the first one here in the top left by 90 degrees, I get the second one, right? So these two wave functions, they have great similarities, and in fact, they have the same energies, and therefore they are degenerate. Here's another one. This is y22. So now both in x and y, the index n equals 2. And you see now in both dimensions, it makes a swing up and a swing down. And you get this very interesting shape of the wave function. Okay, so this is the 2-dimensional wave of an electron that is in psi 22. Now, if I take the modulus square of this wave function, you can see that there are 4 bumps. There's going to be 4 bumps in this particular cavity, in this box. And so those are the locations where you are likely to find the electron. Smack in the middle, there is a node that is location where the probability is going to be 0. Okay, so you will not find this electron in the middle of the box. In fact, most likely you find it at one of those 4 bumps. Okay. So let's move on to this scenario here. So we are considering the case where the barrier is only on one side. So we're moving away from the box, and we are considering the case where I have a potential barrier that is basically starting at position 0, let's say, and then moves on to infinity. So it's a semi-infinite potential barrier. And I'm going to require that this V is not going to 0. Oh, sorry, not going to infinity. Okay, so it's a finite barrier. This is different from the case of the box, because there I said the potential goes to infinity. Here I say it does not go to infinity. So that implies, as we have learned last time, or a couple of lectures ago, that there is a finite chance of finding the particle in the barrier. Okay, that's the so-called tunneling effect. So let's now try to find a solution to this particular case. So here we have a general solution of the wave function on the on the left-hand side. On the left-hand side, remember, V equals 0, okay? On the right-hand side, V is an arbitrary number. Let's call it V0, V naught. So it is a finite value. But here on the left, I don't have a potential, so it's 0, and therefore I have a solution that looks like this, okay? Previously, I wrote an A here and a B where the R is, okay? But now I'm going to make the A 1, and I'm going to write the B as an R. Why? Because the R is going to mean something in a moment. It's going to be called reflection, okay? That's why I call it R. Why do I call it reflection? Because basically, the first part of the wave function, this guy, is really what describes the particle moving to the right, because it has a potential, a momentum of k h bar. Okay, so this part is k h bar, which means it moves to the right. This guy here has also k h bar, but it moves to the left because there's a negative sign. Okay, so basically the first part describes the particle moving to the right, and the second part describes the particle moving to the left. That's why I call this reflection, because if the particle is initially moving to the right, it hits this wall and it bounces back, that is going to be described by the second part of this wave function. Okay, so that's why I'm calling it like that. Was that a question?
Yes, I had a question. Is it by the same magnitude, or is R there to like amplify the magnitude? I don't know if that makes sense.
No,
Like
the
a
R I'm
constant.
going to leave in here, and I'm going to determine what this R is. I'm not going to assign a value to it. I'm going to just find the value based on the physics of this problem. Okay, so R right now is unknown. I'm just going to call it R because it's going to mean something that has to do with the reflection of this wall, right?
Right. Okay, but is the momentum going to be greater to the left then
No.
afterwards?
The momentum is the same because momentum is defined by whatever k is, and both of these parts of the wave function have the same k. So the momentum to the left and to the right is the same.
Okay, I was just a little bit thrown off because you said that the momentum going to that side is determined by e to the ikx, right? But what about the momentum this way? It's also determined by to the left is determined by the e to the negative ikx, right?
Yeah.
But when there's a variable like a scalar next to that number, it just makes me assume that the momentum going to the left is going to be greater than the
No.
momentum
Okay.
going to the
So
right.
let me write it out for you. Basically, let's split this wave function in two parts. Let's call one L, that means left, and one R, which means to the right. Okay. So to the right is going to be this. Okay. And if I'm asking what is the momentum of that part, what I have to do is I have to use the momentum operator on this wave function. Okay, and if you do that, what you'll find is kh times the wave function. Okay, so that means the momentum, eigenvalue momentum is kh bar. Now, if we do the same thing for this guy, it's r minus this value. So I do the same operation. I'm going to operate on it. Oops, sorry, this is PowerPoint writing, very difficult. What I find is minus kh bar, and what I find is actually r e I k x with a negative sign, but this is the wave function, so that equals minus kh bar times this guy. So the r has no effect on the magnitude of the momentum because it's part of the wave function itself.
Right, it's the eigenfunction, as we like to call it, right? It's the eigenfunction.
It's an eigenfunction of the momentum operator. The eigenvalue is this. Eigenvalue does not have the prefactor in it.
Yeah. Okay, I understand now. Thank you.
Okay, so what can we say about this function here? Well, I would like to remind you that k is defined as follows, exactly the same as before. It's 2m e, where e is going to be the energy of the particle over h bar. Okay, so that is the same expression as before. What about the situation here on the right? Well, on the right, we're going to have a wave function that looks a little different. Remember, it looks like a decaying exponential with kappa. Okay, and if you don't remember what kappa was, let me write it down. Kappa is defined, looks very similar to k, but in fact, it has the v in it. V naught minus e over h bar. Okay, so v naught minus e, and here k has only the e in it. So there's a difference. Okay, so k and kappa are not the same thing. So I have now on the left an expression for the wave function, and on the right also an expression of the wave function. Okay, so these are the shapes that I have. And so I would like to solve now for R and T. How do I do that? Well, I can do that if I have the boundary conditions. So one of the boundary conditions is that the left and the right part of the wave function must meet at the barrier and must have the same value, because there cannot be a discontinuity. That's one of the conditions for wave functions. They cannot have a discontinuity. So that means that the wave function on the left at location 0 must be equal to the wave function on the right at location 0. Okay. So if I do that, if I on the left, if I fill out 0 here, 0 in the first part, it's going to be 1. Okay. And 0 here, it's going to be 1 times r. So that's 1 plus r. Okay. And then here on the right, if I put in 0 for x, then the exponent becomes 1 once again, and I get t. So I have here a relation between t and r. 1 plus r equals t. Okay, so that's my first condition. Is there another boundary condition? Well, there is actually. Another boundary condition is, as we saw a couple of lectures ago, that the slope must be continuous everywhere. That means also at location x equals 0. So the slope at location x equals 0 must be continuous. It must be equal on the left, and it must be equal to the left and the right at position x. So if I do that, I take basically the derivative of this function, and then I'm going to fill out x equals 0. So let's do that for the left. And what I find is ik 1 minus r. That is the derivative, the value of the derivative of this function evaluated at location x equals 0. I can do the same thing for this guy. What I find is minus kappa t times 1, because that is what the complex exponent is at this location. So this is the second kind of result that I have. I have now 2 expressions here for t and r. 2 expressions and 2 unknowns means I can solve for t and for r. All right, so let's do that. I'm going to substitute now an expression for t that is given over here in the equation right there. So this is just minus kappa 1 plus r. Okay, now if you do that, it's actually 2 steps, but what you find, it's not hard. You can try it for yourself. You find for r the following: minus k plus kappa divided by ik minus kappa. Okay, so that is the solution for r. And if I know what r is, I can calculate t as well. Okay, so just substitute the following. This is an expression for r in the equation right here. Okay, and if I do that, I can find a solution for t as well. I'm going to rewrite it a little bit to make it look nice, but the answer is going to be this: 2ik over ik minus kappa again. So the denominators are the same, but the numerators are different. All right, so I have an expression for r and an expression for t, and this r is supposed to mean reflection. So what is the likelihood of it bouncing off from this wall towards the left? And this t, the reason why it's called t is because it means transmission. So the transmission through the barrier is indicated by t. All right, so but it's not just r or t, it's actually because the probability is indicated by the modulus square of the wave function, which means it is defined by r squared. Modulus square of r and modulus square of t are the probabilities of transmission and the probability of reflection. Okay. Now, the interesting thing is this is why this is an interesting exercise, because there's a surprising result, as you will see in a second. Let's do that. Let's take the modulus square of this function. What I find is going to be k squared plus kappa squared for the numerator and the same for the denominator. Oh my God. This is writing with your mouse in PowerPoint with the pen tool. Not recommended. this equals 1. Okay? That is remarkable. I don't know if you think it's remarkable. I think it is, right? Because what I was just saying is that I have a wave function here on the left. There's a transmission through this barrier as a complex as an exponent, a decaying exponential, not a complex, but a decaying exponential. Okay, so there's a finite value of finding it here, yet the reflection, the chance of the particle being reflected is always 1. So no matter its whereabouts in this barrier, it will always come out. It will always be reflected with a probability of 1. Okay, so that's perhaps a little surprising. It doesn't disappear. It's not true if it explores this area, this gray area, it can explore it, but it won't stay there. It will come out, okay, with the chance which is equal to 1. Now this t squared, this modulus t squared, is also something I can write. 4k squared over, and this same kind of denominator, k squared plus kappa squared. That's what it says. It's hard to read. Apologies. So in the numerator, it says 4k squared over k squared plus kappa squared in the denominator. Okay. Now the bottom line is that this t squared here is the probability of finding the particle in the barrier is not 0. Okay, because both k and kappa have values. That means I will not have a 0 chance of finding the particle in the wall. There is a chance of finding the particle in the wall. It's just that the chance is not 0. So let me show you this pictorially. So I have this oscillating wave on the left-hand side over here. And then as we just computed, there is a decaying wave function in the barrier. Okay, so it approaches 0 at infinity in the barrier. And we just computed the reflected wave, r modulus square, which equals 1. That means if the particle comes here, bounces against this wall, it will come out with a probability of 1. On the other hand, there is a probability of finding the particle in the barrier. So there are moments that you can find the particle in the barrier, and the distribution is given over here by the wave function. And that is a chance larger than 0, okay, as we just saw, because t modulus square is a value larger than 0. Now there's a name for this. That's called evanescent wave, okay? So we have a reflected wave, chance 1, evanescent wave, chance higher than 0. This is odd, right? But there's actually examples that maybe you are familiar with. So let me give you an example of an experiment you can do at home if you have the tools. Okay, so here's a simple laser pointer. I have a couple of laser pointers lying here in my office. There's one over here. Okay, there's like a little keychain. You can use that if you want. This is just a square beaker with water in it, and if you shine the light in at the right angle, of course, what you will be getting is total internal reflection. And this is something that you probably have done in your physics class. Most people have done this. People don't really think about it, but there's some very interesting physics happening at the interface. Okay, so let's have a closer look at what's going on. This is kind of a blow up. Just bear with me here. You see the arrow is the incoming light. So this whole shady area is the incoming beam of light that bounces off from the surface and goes back. Now, if you do a measurement of the amount of light that you shine onto the interface and the amount of light that comes off, that means that you find 100%. So no light has been lost. Nothing has been lost. Everything that's going to hit this interface is going to come off. All right, there's no loss of light. However, if you zoom in, you will see that at the interface, you have a light distribution on the other end. Okay, so if the other end is air, then there is, lo and behold, an exponential function, decaying exponential, where there is still light intensity to be found very close to the surface. And if you move up away from the surface, that probability of finding light intensity is going to go away exponentially. It's exactly the same as we saw for that particle or electron with that wall. this is for light. We know light behaves like waves. Light is massless. Photons are massless, but they do show exactly the same mathematical pattern as we see for the electron. So light waves and matter waves have very similar properties. This is something you can do quite easily at home at macroscopic levels, because this is, centimeters, millimeters. You can see it with your eyes. We cannot do it with, with electrons, because we don't live in the atomic world, unfortunately. But the physics is the same. So what holds for light waves on a macroscopic scale that we can actually perceive also holds for matter waves on microscopic scales, okay? The scales of atoms and molecules. Okay, I would like to leave it at that. I'm going to leave a little early today, but let me know if you have any questions about this. All good?
Yeah, so I just had a question off this. I just want to make sure I'm understanding this. So you're saying that light does penetrate past the water, right? But it eventually comes back down and gets reflected in the same way that the laser's going out, right? So light goes above and then comes back down.
Maybe you can think about it as follows. If you have light coming in and hitting the interface, you don't typically think of light as like some kind of a fixed particle that is kind of like here now and is going to explore this area and it's going to come back. You think of light as just a distribution of light, a distribution of light. Now, the distribution of light is mostly here. It's going to hit the interface. It's going to come off. But as it interacts with the interface, the distribution in this area is as such. Okay? The interesting thing about the distribution on top is that it is a so-called non-propagating distribution, okay? It's non-propagating, so it doesn't go anywhere. It assumes this distribution, but it doesn't travel in or out, away, or as a function of time. It remains like this. As long as light is there, it assumes this distribution in this vicinity, but the propagation is always in this direction. So this condition only holds at the interface. It interacts with the interface. At the interface, light assumes this distribution, but this distribution is non-propagating. The only propagating part is where the arrows are, and that is what you see. Okay? So think about it as if I am, how can I say this? If I would be an electron interacting with the wall, and I would walk up to the wall. I'm walking, okay? I'm walking. So I'm a moving particle, but then I'm interacting with the wall. I'm actually not moving right now. I'm redistributing myself at the wall. I'm assuming a different shape at the wall, which means I have a little extension in the wall. I have some distribution outside the wall. During the interaction with the wall, this is what I look like. But then my eventual propagation is again me walking away from the wall. So if you think of it as a timed event, then you can think I'm just walking. I'm a purely defined, well-defined particle. I'm walking up the wall, but once I'm interacting with the wall, I'm kind of something different. I'm kind of have a different distribution, and then if I'm coming out of the wall, I'm looking like an ordinary particle again. So it really is at the moment of interacting that I'm kind of something else. I'm something else. I'm not just either propagating or standing still. I have a certain distribution, which is the distribution you find here mathematically for both the matter wave and the light wave. And this distribution here on the other end is called evanescent wave. This is a well-known concept in physics, the concept of evanescent waves, which are so-called non-propagating surface-bound waves. And it holds true for both electromagnetic waves as well as matter waves.
Okay, but those waves do end up going back down, right?
The probability of finding them on this side, on the propagating side, is 100%. Yeah.
Right, and that's what we calculated right now by T, right? Or not by T, but by reflective, right?
The reflection, yes. Okay, but I have to say one thing. I'm going to throw in one little wrench, okay? Because what you can do is this. I can put a molecule here. Okay, a molecule that absorbs light. Let's say a molecule that absorbs light and emits light. So a fluorophore, a fluorescent molecule. You can see it. You can actually measure that, right? And this is something people do. They come in, they do total internal reflection, and the light comes off 100%. But if you put molecules here on the air side, there is intensity. So the intensity can excite the molecule. And as soon as the intensity excites the molecule, that intensity is lost and cannot come out anymore. Because then you have converted the wave into energy at the fixed location, and then it's no longer a wave, and then it doesn't come out. So there is loss of energy in that case on the propagating side, okay? But if you don't put any absorbers in this evanescent field, then it's 100%. So this what I'm just describing actually is a real technology. It's called total internal reflection fluorescence microscopy, which is a well-known tool in biology, in fact. It's a very, I mean, people who use that technique don't really think about it, but it's a very amazing thing.
Yeah, that's pretty cool. I see that. But so in this case, it wouldn't be 100%, right? Reflective, since there is like air molecules and stuff right there.
If you let's say there is a field distribution, so if you have an interaction in this area and you extract energy from the light wave, then that energy is gone and cannot come out. That's right, loss. There's a loss. So if you put a loss mechanism, a loss channel on this air side, okay, for instance, an absorber, a molecule, then there is loss of energy on the propagation side. So then R is no longer 1. It's less than 1.
Right.
But if there's nothing that absorbs, then everything comes out.
Mm-hmm. So would oxygen and nitrogen and basic atmospheric gases interact with that side?
Well, it depends on the wavelength of light, right? Visible light, they will not absorb, right? But let's say infrared light, of course, of certain colors, can be absorbed by gas molecules like CO2 and oxygen, right? They have infrared absorptions. And so, yeah, if you do this same experiment with infrared light, you will see you will not get 100% out because there's some absorption here on the other end.
Cool. And is that another way that we can basically detect how much molecules absorb light, like how much light molecules absorb? I mean, could we possibly do that in that way?
Yes, you can. Mm-hmm. Yep.
Okay. Pretty cool. Thank you.
Yeah. All right, there was a question about discussion sections. Yes, there are discussion sections tomorrow. Discussion sections are happening as usual, except for, of course, on Monday when we had MLK Day. All right, folks, I'll see you hopefully on Friday. Thank you.